This is the third and last part of our discussion on mappings which are of the form z raised to power n and z raised to power 1 over n. So far we have discussed about the square mapping z square and the square root mapping which is z raised to power 1 by 2, and we also discussed about their geometry. Now using the same steps we can discuss the geometry of these kind of mappings for any value of n. So in this session we are going to see how we can do that, how we can generalize that discussion to any value of n. Now once again, if our function is z raised to power n, then we are going to use polar coordinates or exponential form of complex numbers. So in other words, our z is going to be r e raised to power iota theta, and of course z is not allowed to be equal to 0 because we are using exponential form. And we can evaluate this f by taking z is equal to r e raised to power iota theta. So this becomes r e raised to power iota theta raised to power n, which is equal to r raised to power n e raised to power iota n theta. So that's how we calculate the image. Now if we use the same exponential form in the w plane as well, then what will happen? So in z plane we are using complex numbers of the form z is equal to r e raised to power iota theta. Now if we use exponential form in the w plane as well, so let's see what will happen. So if w is equal to rho e raised to power iota phi, then we can compare this w is equal to rho e raised to power iota phi with this f of z, because this is w. Okay, so in other words, this is equal to, okay, so w is equal to rho e raised to power iota phi is equal to r raised to power n e raised to power iota n theta, and we can easily see that this rho should be equal to r raised to power n and this phi should be equal to n theta. So these two equations, that rho is equal to r raised to power n and phi is equal to n theta, they describe this function f of z is equal to z raised to power n, or the nth power function. Okay, so given any complex number z in the z plane, we can calculate its image in the w plane by using these two equations. Okay, so over here we have z is equal to r e raised to power iota theta, and over here the complex numbers are of the form w is equal to rho e raised to power iota phi. Now we can observe that if a complex number is given with modulus r, then it will raise its power n after we applying this map z raised to power n. And similarly the argument of this complex number is multiplied with this number n. Okay, so of course it will be increased, the argument of the complex number will be increased by this factor of n. So let's consider in particular n is equal to 3. In other words, consider this map f of z is equal to z cube. Now if a complex number is given with modulus 1, then if we take its cube, then it will be again the image will be again a complex number with modulus 1. But let's see what will happen with the argument of this complex number. So for example, if this is a complex number and r is equal to 1, and over here we can observe that the theta is equal to 30 degrees. Okay, now if we apply this map f of z, which in this case is z cube, then what will happen with this argument? So we will multiply it by n. So n in this case is 3. So this will be multiplied by 3. So the image of this complex number will have phi, which is equal to 90 degrees. And since r is equal to 1 and 1 cube is equal to 1, so that's why rho will be equal to 1. And of course, if rho is equal to, for example, 2, then under this map f of z, it will be mapped to a complex number with rho is equal to 8. And similarly, if r is equal to 0.5, then it will be cubed, etc., etc. Okay, so that's how we calculate the images under this map z cube. Now let's see the general picture. So if I apply this function f of z is equal to n cube on some region, okay, so this region is has two parts. One part is above this real axis, and it's making an angle of pi by n, and the same reflection of this region below this real axis, and once again the angle is pi by n. And we have colored these regions with different shades so that we know what will happen after we apply this mapping f of z is equal to z raised to power n. Now observe that when we apply this map z raised to power n, then the argument will be multiplied with n. So that's why if we are having this region making an angle pi by n above and below this real axis, and when we apply this mapping f of z is equal to z raised to power n, then we will get the whole disk. Okay, so this is part of the disk and a set of all complex numbers following this angle, and the argument the modulus is less than or equal to 1. So this distance is 1. Okay, and when we apply this mapping, okay, so if r lies between 0 and 1, then of course rho lies between 0 and 1. So every image under this map of this sector will be contained in a disk because rho lies between 0 and 1. And what will happen with the angle, the argument theta? So it will be multiplied with n. So that's why this phi lies between minus pi and pi. So that's why we will get the whole disk when we apply this function z raised to power n on this sector of this unit disk. Now once again we can observe the color regions, and complex numbers in this green region will be mapped to these complex numbers in the green region, and similarly we can follow other colors. So this tells us the idea about the behavior of these mappings. Okay, so it's some kind of expansion of this disk. Okay, so when we apply this thing, so since the angle is multiplied with n, so that's why the complex numbers are kind of expanded to the whole disk. Okay. Now we can talk about the inverse of this map. Similar to the calculations of z square, we can calculate that the inverse of this function is basically omega raised to power 1 over n, and of course we can easily calculate that this is equal to rho raised to power 1 over n and e raised to power iota phi over n. Okay, and this phi is basically the argument or the principal argument of this complex number omega. Okay, so once again, just like we discussed this in the case of n is equal to 2, so over here this phi is the principal argument of this complex number. Okay, so that's why the answer is going to be a unique complex number in this case. Now if we restrict the domain of this inverse map to the whole unit disk, okay, so just like when we applied this z raised to power n on this sector, we got this whole disk. And if we apply this inverse mapping, nth root mapping on this whole disk, then we will get this sector. Okay, so making an angle pi by n on both sides of this real axis. Okay, so if this set is B, then this set B, which is the unit disk, will be mapped onto this sector. Okay, and once again phi is basically the principal argument, so that's why this is going to be a unique complex number. The inverse image is going to be a unique complex number. Okay, so it's an important function, so that's why we name it the principal nth root function. So once again the reason is we are using this argument to be the principal argument or the argument of this complex number. Now let's talk about geometry of the mappings z cube. So we observe that when we apply this mapping z square on this rectangle in the z plane, then we get these kind of shapes which are basically parabolas. Okay, and this whole rectangle will be mapped to this shape, and the top edges are basically parts of parabolas. Now the question is, what will happen if we apply z cube on this rectangle? Okay, now let's see this image. Okay, so when we apply this z square on this rectangle, then we got this image. And if we keep on increasing the powers till n is equal to 3, then we get this image. Okay, so I'm leaving this as an exercise to show that why we get this shape after we apply z cube on the rectangle. And similarly, when we apply z raised to power 4 on that rectangle, okay, so this is the part z cube, and now this is the shape when we apply z raised to power 4 on this rectangle in the z plane. Okay, so once again, I am leaving this as an exercise for you. It is going to be very interesting exercise to show that what are the equations of these top edge and bottom edge, and what are these lines. Okay, so why we get these lines when we apply this mapping z raised to power 4 on the rectangle. Okay. Now let's try to solve some simple questions involving the mappings. Okay, so in this case we considered the map z raised to power 4, and we want to know that the image of the following region under the map f of z is equal to z raised to power 4. Okay, now if we want to calculate that, then once again we are going to use this exponential form, and the exponential form when we apply this mapping becomes r raised to power 4 e raised to power iota 4 theta. Now if we want to know the image of A under this map f, then we want to know what will happen with the modulus and the argument of a complex number. Okay, so we can observe that the modulus will be raised by a power 4 and the argument will be multiplied by a factor of 4. So what will be the effect? Okay, so now in this case, what is this region? So this region is basically in the z plane, a set of all elements for which r is greater than 2. Okay, so in other words, if this is the circle r is equal to 2, if this is the circle r is equal to 2, then the set A consists of all complex numbers. Okay, so complex numbers which are outside this circle, not all complex number. Now the second condition will tell us what complex numbers are contained outside this disk. Okay, so in this case the condition on the argument is it should lie between pi by 4 and pi by 3. Okay, so if this is the angle pi by 4 and this is the angle pi by 3, okay, so if theta is equal to pi by 3 for this case, then we are considering, or this set A is basically set of all complex number inside this partial sector, because these complex numbers are not included. Okay, so these blue region is not included, but this region is included, which lies between pi by 4 and pi by 3, and of course the modulus is greater than 2. Now if we want to calculate its image, then we should know what will be the value of rho. So r square, if r is greater than 2, then r raised to power 4 should be greater than 16. Okay, so in other words, we have one condition on the image or the complex number in the W plane, so which describe the image of this set A under this map z raised to power 4. So this is the first condition on the modulus. Okay, so in other words, if this is the disk, or this is the circle with rho is equal to 16, then our image lies outside this circle of radius 16. Okay, so but what will be the value of argument? This will decide what elements are included in the image outside this circle of radius 16. Okay, now let's start from the range of argument in the z plane. So the argument lies between pi by 4 and pi by 3, and if we want to calculate what will happen with this with the complex numbers after we applying z raised to power 4, then we should multiply it by 4. Okay, so if we multiply it by 4, then we get 4 pi by 4 less than 4 theta less than 4 pi by 3. Now this 4 theta is basically phi. So the image is basically complex numbers for which phi lies between pi and 4 pi by 3. Okay, so what kind of complex numbers lie in the image of this set A then? So let's say this is the W plane. Okay, so we observe that the elements should be outside this circle of radius 16, and phi lies between pi and 4 pi by 3. And note that this inequality, so that's why phi is not equal to pi and phi is not equal to 4 pi by 3. Okay, so in other words, this phi is dashed and it is not included in the image. Okay, and this is if we convert this into degrees, then this is basically 240 degrees. So in other words, so our image lies between these two rays, but they are also outside this circle of radius 16. So the images are going to be these complex numbers. Okay, so outside this region. So this is the image under this map z raised to power 4 of the set A. Now let's consider another example, and this time we choose the mapping the fourth root, or z raised to power 1 by 4, and try to calculate the image of this sector defined by these conditions under this map. So this is set of all complex numbers. Okay, so there is no condition on R now, it's just R is greater than 0. And there is a condition on the argument, it should be greater than minus pi and less than 2 pi by 3. And we want to know the image under this map of this region. Okay, so the map is z raised to power 1 by 4. So that's why when we apply this map on this exponential form of a complex number, then we get r raised to power 1 by 4 and e raised to power iota theta by 4. Okay, and if we use polar coordinates, w is equal to rho e raised to power iota phi in the w plane, then we get the following condition. Okay, so since r is greater than 0, so that's why r raised to power 1 by 4 will also be greater than 0. And this implies, since rho is equal to r raised to power 1 by 4, so that's why we can say that the image in the w plane of this region has rho greater than 0. Now let's see what will happen with the argument after we apply this map z raised to power 1 by 4. Now the given sector has the following range of the argument. The argument lies between minus pi and 2 pi by 3. And now if we divide it by 4, so why we are dividing it by 4? Because we know that in the w plane, rho is equal to theta by 4 under this map z raised to power 1 by 4. So that's why we divide these inequalities by 4 and we get the following inequality. And this implies that our phi lies between minus pi by 4 and pi by 6. Now we have the knowledge of both modulus and the argument in the w plane of the image of this sector under this map z raised to power 1 by 4. So what is the image? So it consists of all complex numbers for which rho is greater than 0 and phi lies between minus pi by 4 and pi by 6. And we can easily sketch this region in the w plane as well. We have discussed about these special kind of power functions, which are nth power functions and nth root functions. And we studied about their geometry. In other words, we studied what will happen if we consider regions in the w plane, what will happen after we apply these mappings on those regions. Okay? So they have some very interesting geometrical properties.